OSI model. And the layer which is coming below the transport layer is the network layer. And the network layer is the one which is ensuring that the source to destination packet delivery happens. So when the packet reaches from the source to the destination, in order to understand what the purpose of the transport layer is, if you look at the purpose of the transport layer, it is the transport layer that ensures that the data reaches correctly at the other end. So the data reaches correctly at the other end means we will be ensuring through the transport protocol, we will be ensuring that the quality of service is maintained. And the transport layer is actually the true end-to-end from the source to the destination. And when you look at the layers of the OSI model, we can say that the layers 1 to 3 are chained and the layers 4 to 7 are end-to-end. So the layers 1 to 3, that is the layers below the transport layer, starting from the physical layer, the data link layer, the network layer, all these layers, they are host-to-host packet delivery service. And this host-to-host packet delivery service has to be turned into a process-to-process communication channel, mainly because on a single host, we'll have many applications, many processes, many services running. And so you have to identify when you are delivering the packet at the destination, we should know to which process you are delivering the packet to. So an end-to-end protocol which supports the communication between the end application programs is required. And this is a function of the fourth layer, which you call the transport layer of the OSI model. So when you look at the transport layer, it is shaped in such a manner that its higher layer is demanding something from it. It is expecting some service from the lower layer, which is the transport layer. And the transport layer will in turn get it done from its lower layers, that is the network layer and the link layer. So if you look at the limitations of the network layer, you will know what exactly the transport layer should do in order to cater to the services that the application requires. So you are looking at the limitations of the network layer. These are the main limitations of the network layer because the protocol that is running in the network layer is called the Internet protocol. It is just a best effort protocol. It is an unreliable protocol mainly because it is connectionless, because of which there are every chances that it will drop packets. The packets will be reaching out of order because individual packets take different routes to reach the destination. So the one which is going through the shortest path will reach first. The one which is going through a congested path may be reaching, even if the route is of shorter distance, it may be reaching later. So because of which there is a reordering which is required at the destination. And then there are every chance that we'll have duplicate packets because we may be getting duplicate packets at the receiver. So those duplicate packets has to be avoided. And there is a limitation that the messages will be of finite size depending on the transmission media. And then it may take an arbitrarily long time for the delivery of the messages. All these are the shortcomings of the network layer, which is the layer lower to the transport layer. So the challenge is for the transport layer, the challenge is to develop algorithms that turn the less than desirable properties of the network layer into a high level service which is required by the applications. The applications that is the layer which is the higher layer to the transport layer. And in order to extend the host-to-host delivery service provided by the network layer, I'm trying to extend the host-to-host delivery service to a process-to-process delivery service because I'm not just interested in the host, but the application that is running in the host. So many services may be running in a given host, and the protocols need to have a multiplexing, demultiplexing action that is going to allow each application to share the network. So when we talk about multiplexing, multiplexing is that which is happening in the sender side. So when you are multiplexing means there will be different applications that will be running on a host machine. So the header part will surely have some indication of which application it is. So in the transport layer, the header will have a port number which identifies the service. Similarly, at the receiving side, there will be port number which clearly identifies or determines which application should receive the data that is being sent by the sender. So a multiplexing demultiplexing action takes place by means of the ports. So if you look at the transport layer, there are 5 functions that the transport layer will do. It is the port addressing, segmentation and reassembly, error control, flow control, and connection control. If you look at port addressing, you know what is port addressing because it is the port numbers that identifies the different services depending on the applications. And it ensures that the data is correctly directed to the appropriate application on the destination machine, on the receiving machine, because there is a possibility that on the receiving machine there will be several processes run on that particular machine. And the second function of the transport layer is segmentation and reassembly. Why do you need segmentation? The message that the application is giving to the transport layer to be sent down the layers and then through the transmission media up to the application on the receiving side, that message may be very large and it has to be divided into transmittable segments on the transport layer. So this process is called segmentation. And these segments are transmitted individually and they may take different paths to reach the destination. So each segment has to be identified by means of a sequence number. And at the destination, reassembly has to happen so that the entire message is given to the application. So that process you call the reassembly. So in this process of reassembly, if any of the segment is missing, we'll know that a segment is lost, and because of which we'll not be able to reassemble and get the entire message back. So we'll know that there is a corruption that has happened in the message and we'll ask for a retransmission. So all these are the duties of the transport layer. Segmentation and reassembly is necessitated because most of the time the application will be sending a large message which will not be transmittable over the transmission media as such, and it will be difficult to handle by the different layers because there is a specific length for each one of the, starting from the transport layer. For the segment there is a maximum size, for the network layer, for the packet there is a maximum size, for the data link layer, for the frame there is a size limit. And the third function that the transport layer will do is the error control, because the transport layer is detecting the errors. What are the errors? It is the lost segments or the corrupted data. When the segments are lost, it is the corrupted data. So it requests for a retransmission of the lost or the erroneous data. That is the error control that is being done, and error control is required to have the data integrity because the transport layer ensures end-to-end error control. Between the source and the destination, it will see to it that the data integrity is maintained. And then the fourth function of the transport layer is connection control. What do you mean by connection control? The transport layer can be either connectionless or connection oriented. We know the two protocols that are running on the transport layer are the connectionless protocol, which is the UDP, and the connection oriented protocol, which is the TCP. So in the case of a connection-oriented protocol, that is the TCP, the transport layer has to establish a connection. It has to establish a connection and manage the connection between the sender and the destination. So this only will ensure that the data is reliably delivered and received, maintaining the order of the packets. So this is being taken care of by the transport layer with the protocol TCP, not with the protocol UDP. And the last function of the transport layer is the flow control. Flow control is to ensure that the receiver, even though the receiver will not be of the same speed as that of a transmitter, the receiver is not overwhelmed. And also the network is not congested. So these are taken care of by the transport layer. So if you look back, you will see that these functions of error control and flow control are done in the second layer, which is the link layer. But what is the difference in the case of transport layer is that it is doing an end-to-end error control and end-to-end flow control. We'll see the details later. So if you take the transport layer, there are two protocols. The one is the TCP and the other is the UDP. So the two important protocols are the UDP and the TCP. So we'll take one by one. We'll take the simplest protocol, which is the UDP, which is a connectionless protocol. But the minimum, it'll do only minimum functions. The minimum functions that are required is in the transport layer, we have to identify the process for which multiplexing and demultiplexing is required. Multiplexing and demultiplexing is required to ensure the correctness of the message and, in order to ensure that the correct process is reached at the destination. And then the other essential thing to do in the case of a transport layer is that the correctness of the message is ensured. If there is anything missing, any corruption happens by means of missing of the segment, it will ask for a retransmission. So that is being ensured by means of the checksum. It is through checksum that the error control is done in the transport layer. So UDP will have the multiplexing, demultiplexing action by means of the ports, and also it will have the checksum. That is all. The flow control is not done. The reliable ordered delivery of the segments is not done. None of these are being done because UDP is a very trivial protocol. So UDP, the basic function is that the source process has to send to the destination process. So if you look at the UDP header format, header has just 4 fields. One is the source port, other is the destination port, other is the length of the datagram as such, and then it is the checksum, and the remaining part is the data. So this forms the header. The first 2 words, we call it word. One row, you call it a word. A word is a 32 bits. Word corresponds to 32 bits. So you understand that the source bits will be 16, destination bit will be 16, and then the length will be 16, checksum will be 16. So if I take row wise, this one row is 32 bits, this one row is 32 bits, and then you have the data, which is of variable length. So UDP is an unreliable connectionless service. UDP has only 4 fields, each consisting of 2 bytes, isn't it? 2 bytes. I said it is 16 bits, 16 bits, 16 bits, and 16 bits. So it is 2 bytes. That is 4 fields, each consisting of 2 bytes. And UDP has ports which are 16 bytes. With 16 bits. With 16 bits, how many unique ports can be there on one host? You will have, with 16 bits, you will have 2 raised to 16 possibilities. 2 raised to 16 is 65,536. So you can say it is 64K possible ports are possible. You can have 64,000 or 64,536 different applications running on a host. Okay, so the source port is the one which indicates the port number on a sender device, identifying the application or the process that is sending the data. Correspondingly, you have a destination port which specifies the port number of the recipient device, identifying the application or the process that should receive the data. So how will the process learn the port, which port to send the message? So if I am taking, I'll just take an example of a client server communication that is happening. The client is the one which is initiating the connection. So client will know what service it wants from the server. So what the client will do, client will initiate a message exchange with the server on the server's well-known port. On the server's well-known port. You know about the well-known ports? Actually, ports starting from 0 to 123 are the well-known ports. If I just take the port number 20 or 21, they correspond to FTP, File Transfer Protocol. 22 is Secure Shell, SSH. 23 is Telnet, Remote Login. 25 is SMTP. 53 is domain DNS. 80 is HTTP. Likewise, you have. So the client will know what service it wants. So it will connect to the server, its IP address, and to the port, which is a well-known port. So all the services, known services are, all the known services will be between 0 and 1023. That is 1024 different ports, which are the well-known ports which are run on the server. So the client will initiate a connection on the server machine on a well-known port. And when it initiates a connection, the information of the client, its IP address, along with its port number, will be known to the server. So the server will reply if it is willing to share, if it is willing to initiate the communication, it will communicate with the client. And then now the client and server has communicated. Now what they'll do is they'll agree upon some port number so that the well-known port is freed and the other clients can use the well-known ports. That is how a communication, a client-server communication happens. When I say a port and freeing a port, it is just an abstraction. Just understand that it is just an abstraction. And with the ports, the UDP is supporting the multiplexing and the demultiplexing mechanism. And that is the simple UDP protocol. Now we'll see a TCP protocol. A TCP, it is a reliable, connection-oriented byte stream service. It is a full duplex protocol, and it does, in addition to all the demultiplexing, multiplexing, and the error control, it will do the flow control also. What is flow control? Flow control is a mechanism that limits how much data the sender can transmit at a given time without overwhelming the receiver. So it mainly uses transport layer mainly uses congestion control mechanism, which will limit too much of data from being injected into the network. And the algorithm that is used by TCP in order to do the flow control is a sliding window algorithm, where you have a window, you will be sending it and will be waiting for the acknowledgement. As in when the acknowledgement is received, you will vary the window size. You can have more of data being sent from the sender to the destination. If there is no congestion, the window widens. If there is too much of congestion, when the acknowledgement is not received properly, you will reduce the window size. We'll see the sliding window algorithm later. So this is how a TCP header format will look like. Just look, you have a source port, you have a destination port, both of 16-bit. So each one of these lines are going to be 32 bits. You call it a word. You have a sequence number, which is 32-bit. You have an acknowledgement number, which is 32-bit. You have a header length, which is 4 bits. You have reserved bits, which are 6 bits. You have flags, 6 of the flags, 1 bit each. So totally 4 plus 6, 10 plus 6, it is 16 bits, correct? Then you have an advertisement window, which is 16 bits. You have a checksum, which is 16 bits. You have an urgent pointer, which is 16 bits. And then you have a option field. It is not mandatory. It is variable in size, but it has to be 32 bits. If it is not 32 bits, you will have to pad it with zeros to make it 32 bits. And then you have the data. We'll see each one of these fields in the TCP header. So first thing is the source port, 16 bits. You know the purpose of the source port. You know the purpose of the destination port. And these are to identify the processes which are running on the source and the destination respectively. And the ports uniquely identify the ports along with the IP address uniquely identify a connection. So when you have a connection between the source and the destination, between the same source and the destination, there can be more than one connection because different applications are running. So normally you identify a connection by means of a four tuple, that is source port, source IP, destination port, and destination IP. And then you have a sequence number. Sequence number is 32 bits in length. You have an acknowledgement number which is also 32 bits in length, and you have an advertisement window which is 16 bits in length. All this correspond to the sliding window algorithm. All this correspond to the sliding window algorithm because TCP, it is a byte-oriented protocol. Each byte of data has a sequence number. Each byte of data has a sequence number. So when you have the sequence number field, the sequence number field, it contains the sequence number of the first byte of data which is carried in that segment. So it helps in arranging the segments at the receiving side because you will be receiving the segments and you have to do a reassembly. So depending on the sequence number, you will be doing the reassembly. And then you have an acknowledgement field, which is also, acknowledgement number, which is also 32 bits. When you are sending an acknowledgement for a packet that is being sent, normally what happens is that along with the acknowledgement, you will be sending what you are expecting next. That is the sequence number of the next byte that is to be transferred to the receiving machine. So the acknowledgement number will have a sequence number which corresponds to the segment which is to be sent next. So it will be a 32-bit number. And then you have the header field, which is 4 bytes in length. The header field is 4 bytes in length. That is, 4 bits in length. That is 2 raised to 4 or 16. You can have 16 32-bit words for the header. This is one word. This first line is one word. Second sequence number is second word. The acknowledgement is third word. This totally forms the fourth word. This checksum and urgent pointer together forms the fifth word. And then, since there is a possibility of the header to have 16, the options can be 11 words maximum. It is not necessary. So the header length will be essentially it should have this 5, and then it can vary from 5 to 16. So that is about the header length. After header length, we have the reserved 6 bits. It is not normally used. It is used for future. It will be used for future, and hence, right now we are not using it. So we will set all the bits to 0. We'll make all the bits 0 because those are the reserved bits. And subsequently, after this, we'll have the flags. Flags are 6 in number. We'll see each one of the flags. There are 6 flags. First is the SYN flag, synchronized flag, to establish the TCP connection. And to terminate the TCP connection, we have a FIN corresponding to the finish, terminate the TCP connection. And then we have the reset. Once we see that the receiver is somehow confused with the connection, it may try to abort that connection by means of setting the reset flag. There can be a push, there is a push flag which is giving an information to the receiving side. It is invoking that a push operation to notify the receiving process that I'm pushing some information to the receiving side. There is an urgent flag which is set, which says that the segment contains some urgent data, and that urgent data will be up to the urgent pointer bits. And then there will be an ACK flag which corresponds to whenever there is an acknowledgement corresponding to a data that is received, we'll have this act flag as set to high. And the remaining fields are the advertisement window and the urgent pointer. We'll see that the advertisement window, the window size is 16 bits. So this is very crucial for the flow control. What it does is it gives an indication of the size of the sender's receive window. It will just say that this is the buffer that I have. Do not send me anything more than this size, because then the buffer overflow will happen and I'll not be able to receive the data. So it specifies how much data in bytes the sender can receive before requiring for an acknowledgement. So if that acknowledgement is not received, it will stop and it will wait. Till that time, I can send that window size of data waiting for an acknowledgement. So that will be the receiver's buffer size. So if the sender is fast compared to that of the receiver, or if the network is congested, we make use of this flow control. So a small window size ensures that the sender does not overwhelm the receiver, or the network is too congested and will not be uh, pumping in more of data, so that the network is congested and no traffic traffic happens. And the checksum, as you know, you have already studied what a checksum is, corresponding to the CRC that is there in the link layer. We have checksum in the case of the transport layer. It provides error checking for the header and the data. It ensures the integrity, because if there is an error, the transport layer will be asking for a retransmission. So it ensures the end-to-end integrity of the data. And the last field is the urgent pointer. With the when you are setting the urgent pointer, it indicates that the segment contains the urgent data, and this field specifies where the urgent data ends. So it is still the urgent pointer that you have the urgent data. It is informing that the data is urgent till the urgent pointer data. So that is how it is. And other than that, the last field is the options field. Options field includes a lot of things like the maximum segment size, window scaling, the timestamps, so on and so forth, which are not mandatory. But these option field, they provide additional information for the TCP connection. And this is just optional. And its length decides the header length. We know after the 5 words, it is the options field. So you can have, starting from the 6th word to the 16th word, you can have the options field. And that decides the header length. And if it is not forming 32 bits, what we do is we pad it with zeros to make it 32 bits. That is how it is. So that talks in entirety of the TCP UDP header, the TCP header. So what we have seen are the functions of the transport layer, the two protocols, the UDP and the TCP, and the header of UDP and the header of TCP, and each one of the fields. So, now we'll be seeing how a connection is being established, how a connection is being terminated in the case of a TCP in the next class.